Right, we're going to talk a little bit about absolute value functions. We're going to remember that absolute value functions can be written as piecewise functions, and we'll talk about that more at the end of this video. I need you to remember that graphs of absolute value functions that we do this year are going to be V-shaped. There'll be two rays hooked together at a common endpoint called the vertex. They're V-shaped and they have a symmetry line that goes through the vertex. And our symmetry line is going to be a vertical line through the vertex. So all of our absolute value functions are going to open either up or down. The vertex form of the absolute value function equation is y equals a times the absolute value of x minus h plus k. hk is the vertex, and we call it the vertex form of the equation because you can see the vertex from the equation. We're going to talk about what these pieces of the vertex form of the equation do. So the a, if a is bigger than 1, there's going to be a stretch, a vertical stretch. Vertical stretch. If a is less than -1, there's going to be a reflection and a vertical stretch. Because if a is negative, if a is less than 0, there's going to be a reflection. It's going to flip the V shape upside down. So if a is less than 0, there's a reflection. There's a stretch if a is greater than 1, or if a is less than -1, vertical stretch. If a is between -1 and 1, there is a shrink. So as we said, the a controls the slope of the sides of our absolute value. The h is our horizontal translation. Horizontal translation. Okay. And the k is a vertical translation. And I'll point to the k. He's the vertical translation. All right. We're going to take a look at an example, talk about how to graph an absolute value function that is already written in vertex form. But we're going to look at it just a little bit differently because I want to look at that x plus 2, this x plus 2 that's inside the absolute value. I want to look at that as being x minus -2 so that I can see my h value. There's x minus h, so h is -2. We're going to look at the -3 as being plus -3 so that we can see our k value. So h is -2. K is -3. The absolute value of x minus h plus k. All right, we're going to do a graph, then we'll identify the domain range. I'm going to create a table of values for this function, for this equation. And our equation is y equals the absolute value of x plus 2 with a -3 outside here. I'm going to put the vertex in my table, -2, -3. And notice we plug in -2 for x, we do get -3 for y. Since that's the vertex, what I'm going to do is take some values that are bigger than -2, x values that are bigger than -2. Find the y values that go with them, and a couple of x values that are smaller than -2. And we're going to use the symmetry of this as well. So if we plug in -1 for x, look at what we get. -1 plus 2 is 1. The absolute value of 1 is 1. 1 take away 3 is -2. If we plug in 0 for x, we get the absolute value of 2, which is 2. Take away 3, which is -1. Now, if we have the right vertex, when we plug in -3, we should get the same y value that we had when we plugged in -1. Those should have the same y value because they're the same distance from our symmetry line that goes through the vertex. So let's see if we do. -3 plus 2 is -1. Absolute value of that is 1. Take away 3 is -2. Look, it worked. We got the same y value for -3 for x equals -3 that we got when x was -1. We plug in -4, we get -1 again. So I'm going to put my vertex on the graph. -2, -3 is my vertex. We've got -1, -2. We've got 0, -1, and it would keep following that slope of 1 on this side. Notice how it's a slope of 1. Up 1, right 1, that's a slope of 1. And on the other half of the graph, we'll plot the point -3, -2. We'll plot the point -2, -4, -1. And then -5, 0. And we're over on this left half of the graph, we're following a ray with a slope of -1. All right, we're going to identify the domain and the range. Notice that the domain of this is all real numbers. We can use the capital R with the extra line, or you can use the phrase all real numbers. And the range is everything greater than or equal to -3. Notice the smallest y value was happening at -3, and we get all y values greater than or equal to -3 for our range. Now we're going to write the function g as a piecewise function. Notice the change is happening at x equals -2. That's where the change happens for the two different rays. We switched from y equals, let's see, the left half. So for the left half, y equals mx plus b, where x is less than -2. We have a slope of -1 on the left side. We go down 1, right 1. That's a slope of -1. So -1 times x plus b. Well, we don't have the intercept, but if we continued on the path, with a slope of -1, we'd go from the vertex to the point -1, -4 to the point 0, -5. So we could actually find that y-intercept by just counting. So 1/2 of our graph is given by the equation y equals -x minus 5. That's for x less than -2. And then if x is greater than or equal to -2, the other piece of the graph, we're following a line with a slope of 1. And as we follow that line with a slope of 1, over here on this piece, the right side, slope is 1, positive 1, and the y-intercept is -1. So we're looking at y equals x minus 1 if x is greater than or equal to -2.